Okay, so we remember now that how voicing works with the vocal folds. We remember that it's a cycle that repeats over and over again. And because it's a repeating cycle, in terms of air pressure, it creates a repeating wave that repeats over and over again, uh, propagated in terms of air pressure. That wave largely determines the perceived pitch of linguistic sounds, so low pitch, high pitch. Uh, there are a couple other things that go into the perceived pitch of a sound, but mostly it's that source wave of your glottis vibrating, and that wave or the frequency of the wave is known as the fundamental frequency of a sound, abbreviated F0. This is a pretty important measurement. And yeah, so the difference here is that pitch is a mental phenomenon. It's a perceptual thing that people hear, low, high. Fundamental frequency is a physical property of a sound. It's an acoustic property that you can measure with instruments. Now, in most cases, how high or low you perceive a linguistic sound as being pitched is going to mostly depend on the fundamental frequency, on the F0 of that sound, but know that that matchup is not entirely perfect. For the purposes of this class, we can sort of use the two interchangeably, say high pitch, high F0, low F0. They kind of mean the same thing. If we were doing some tricky applications, we might need to distinguish between the two. So F0 is the fundamental frequency of the linguistic sound. It corresponds to the speed or the frequency at which your glottis is vibrating as you speak. And note that that means that only voiced sounds have F0. So voiceless sounds like s or something like that don't have F0 at all. Whether or not they have perceived pitch is a more complicated question, but these don't even have F0s because they're not repeating waves because your glottis is not vibrating, right? Okay, so earlier we said that F0, you can think of that as coming from the wave that we looked at. That could be, the position of the vocal folds or the air pressure behind them or something like that. And that is a useful way of thinking about that wave and why it has the F0, that's the frequency of your glottis vibrating. But actually, that model is a little bit of a simplification. And so here's what's really going on there. This is going to become important in a moment. This is a perfect sine wave. It just shows the overall glottis, say, moving this way, then moving this way, then moving this way in an ever-repeating cycle, and it makes this beautifully shaped repeating sine wave. Human tissue, however, does not move like that. Human tissue is imperfect. It has lots of irregularities and little bits and interconnected parts, and each one of those little bits of tissue can change shape and can change stiffness while it's vibrating. Human tissue is messy. It's not like an illustration from a physics textbook, and of course our vocal folds are not perfectly uniform or symmetrical or anything else. What does that mean? Well, the main body of the vocal folds might be moving back and forth. There's going to be all sorts of other little jittery motions and vibrations and other sorts of things running back and forth within each piece of tissue. And so the real waves that come off of your glottis, right, when you're voicing, when you're vibrating that glottis, they're going to be kind of bouncing off of each other and up and down the vocal folds and causing interference patterns, and they're going to be way more complex than just that simple sinusoidal back and forth motion. So in the Ziga text, she gives an analogy which is kind of useful, and it's the idea of a father bouncing a kid. And so the kid's going up and down, but they're on a moving boat, and the boat's pitching back and forth and going in different directions. And if you track the position of the child over time, it's not going to be this perfect up and down motion. Of course, that will go into the wave. You might be able to see it if you track that, but also the boat itself and its motion and all the little pitches and movements are also going to show up if you're tracking the position of the kid over time. And that's sort of the analogy she gives to how the vocal folds move. The details of how this works obviously are going to be incredibly complicated, and I don't even know how it works, But what's important is the upshot. So what does this mean? Well, instead of a simple wave, a sine wave like the one we looked at earlier, you don't get that. Instead, you get the vocal folds outputting energy at their F0, their fundamental frequency, plus every other frequency that's a multiple of the F0. Right? That's because these are imperfect physical objects, and in nature, we don't really have any perfect sine waves. Everything is pretty much works like your vocal folds in this sense. Right? The closest thing we can get to a perfect sine wave is probably going to be a tuning fork. I don't know if any of you are musicians or have seen tuning forks before. It's a little piece of metal that you bang against something, and it has a characteristic frequency that it vibrates at. And it pretty much only vibrates at that frequency because this is almost a perfectly uniform and even piece of metal. They're manufactured to be that way. Of course, even a tuning fork is not perfect. There's going to be some other kinds of motion in there, but that's about as close as you'll find to a perfect sine wave in the world around us. And every other physical object that isn't perfectly uniform and symmetrical and everything else is going to be not like a sine wave. And this certainly includes parts of your body like your vocal folds. Okay, so we're getting energy from the glottis at the fundamental frequency, F0, plus every other multiple of that F0, right? So if my glottis is vibrating 120 times a second, the F0 is 120 hertz, there's also going to be some energy coming off of my glottis at 240 hertz and 360 hertz and 480 hertz and so on and so forth. Those multiples that are above the fundamental frequency are referred to as harmonics. And those types of vibrating bodies or motions that work like this, like your vocal folds, are referred to as harmonic oscillators or harmonic motion. Right? So this is a very basic kind of object in physics, and most of the things around us in the natural world that we can see and hear are harmonic oscillators. This includes just about every kind of instrument, and in fact, many instruments, the sort of difference between why does a piano sound this way and an organ sounds this other way has to do with the properties of those harmonics, with how loud or quiet they are at different multiples, right? So this is a very basic characteristic of most sounds in the natural world. So the vocal folds are going to output energy or pressure waves, however you want to think about this, into the cavity above them, that is your vocal tract, not just at the fundamental frequency, but at every multiple of that fundamental frequency. So when we're looking at waves in, say, a computer program, it's not enough to look at the fundamental frequency. We're going to want to try to track how much energy there is in different harmonics. And that kind of a graph or a plot of how much energy there is at different frequencies in a complex wave is referred to as a spectrum. So this is a spectrum of a simplified and simulated glottal source wave. Right? What is this showing you? Well, this simplified wave has a fundamental frequency of 100 hertz and 4 harmonics on top of that at 200, 300, 400, and 500. Furthermore, because it requires more energy to set a column of air vibrating at a higher frequency, there's going to be a little bit less energy at each successive harmonic here. So getting the air in your vocal tract to vibrate at 100 hertz requires a certain amount of energy, and getting it to vibrate at 300 hertz requires a lot more energy. So because your vocal folds are a single object and they're putting the same energy at every frequency, you're going to end up with smaller amplitude at each of these higher frequencies. Basically, it's harder to make things vibrate faster than it is to make them vibrate slower. What that means is that rather than a series of identical lines at each harmonic, your power spectrum is generally going to decline as the frequency goes up. On the vertical axis here is the amplitude. It's essentially how much energy or how much displacement there is at each frequency. And so that's going to be higher at lower frequencies. Here's the F0. It's this first line. We're saying this has an amplitude of 1. And the units here are not really important. It's not something you need to worry about. Just, there's some unit of amplitude that we're measuring here. At the first harmonic, it's going to be a lower amplitude. At the second harmonic, 300 hertz, even lower, and so on and so forth, until eventually you're going to get up to a harmonic that has such a high frequency that your folds just won't be vibrating energetically enough to really excite any wave-like motion at that frequency. So eventually, in the real world, this harmonic spectrum is going to eventually just flatten out and be indistinguishable from zero. In theoretical physics, where everything is in a perfect vacuum and there's no friction, this function would go on forever up to the highest frequency you can imagine, right? With one complication from quantum physics that I completely ignore here. Okay, so now would be a good time to check out the audio demonstration in Prot with simple and complex waves and spectra. And I'm just going to basically, I actually made each one of these harmonics and the fundamental frequency, and I'm just going to show you what happens when you add them together.